So I'm Jeff Phillips, and so I'm giving a talk for ESA 2021, finding an approximate mode of a kernel density estimate. This is joint work with Jasper Lee, with Jerry Lee, and with Chris Musco, and with Ming. Okay, so we'll start the problem. So kernel density estimates and the use of kernels to understand data is quite pervasive. We'll start with a point set P, that's going to be an RD, and then a kernel, which is this. So bivariate function takes 2 points and it says kind of how similar those 2 points are. And we will be focusing entirely in this work on the Gaussian kernel, which is probably easily the most kind of common kernel to be worked with. Notice that there could be a covariance structure and often a normalization term. For the work we will talk about, those are not important. They can be, if you do have those, you can pre-process the data by scaling and remove that component. Okay, then a kernel density estimate is going to be kind of the averaging of applying a kernel to every point and evaluating at another here. So I have a point set P, and I want to evaluate at X. Well, I look at the average effect of the bivariate function with every other kernel, or you can think of it as kind of turning a discrete distribution into a continuous one by replacing every point by this smooth kernel, and then kind of averaging all those together. This is really was the large focus of statistics in the 70s and 80s and 90s of turning a discrete distribution into one that's continuous. And there are a bunch of statistical tests, say based on this maximum mean discrepancy and kernel distance. It's really also the foundation of most of nonlinear machine learning, kernel SVM, kernel PCA, kernel k-means, kernel ridge regression. Basically, you replace the Euclidean inner product with the kernel, often using the Gaussian kernel, and you get these nonlinear methods in data analysis. And so those objects are really looking at the kernel density estimate, possibly with science. So this is a really fundamental object to study. Today, we are going to look at what has mostly been an unstudied problem for the most part, at least from a formal point of view, which is the mode, which is the point that has the highest function value of the kernel density estimate. So the argmax over RD of any point X when I evaluate this kernel density estimate. And calculating the mode exactly seems pretty hard. Would be this challenging sort of numerical problem. So we're going to do an approximate finding of the mode. We want to find a point X hat, which has function value within 1 minus epsilon factor for some small error parameter. So epsilon. Okay, and this will be the goal of the talk. How efficiently can we do this? And this is direct applications in localizing and tracking objects, outlier detection, determining multimodality, and robust TDA, where this is an operation that actually has to be performed here. So how hard is it to find the mode of a kernel density estimate? Here's some simple things we know. Well, the kernel density estimate is Lipschitz. If you move the evaluation point a little bit, it doesn't change much. The mode must be near some other data points, so I don't have to look too far from my data. And the mode must be at least 1 over n, because at a data point, that kernel is of height 1. Remember, I didn't have a normalization factor. And so then even averaging everything else to 0, it must be at least 1 over n. Putting these together, I can do something very simple. I can put down a grid that is close to all the points and evaluate these grid points. But this would give us a runtime of something like n to the d plus 2 squared over epsilon to the d. This really is not going to be a great sort of runtime, a pretty high polynomial here. And so we aren't going to want to do this. In 1D, you could probably get something like this to work pretty reasonably efficiently. In 2D, there is some prior work. This was for a slightly more complex problem, but Agarwal, Kaplan, and Sharir noticed that this cool idea where you could sample a point, and then you sample a radius somehow depending on the distribution of the kernel, and whether a point is inside that ball or not, is an unbiased estimate of the KDE. So if it's an unbiased estimate, well, you do this a bunch of times. I sample points and then a radius, and then I count how many of the balls, what fraction of the balls is a query point in, and that determines, that can approximate, converges to the function value of the kernel density estimate. And so then to approximate the maximum, I just have to try and find the point of the highest depth, the point that's in the most of these disks, right? And so in 2D, with this, you can get a runtime of n over epsilon to the fourth log cubed n. But in higher dimensions, this goes up exponentially in D. So this doesn't scale well in higher dimensions here, but it gives us an algorithm in low dimensions. Okay, and another perspective, and oh yeah, and a lot of things based on these depth queries where you can convert it into this, these seem to be pretty hard in higher dimensions. They seem to grow exponentially in D, even with axis line rectangles have been studied more, and that one is better indications that it is indeed hard. Okay, another question is, how many local maximum are there? Let's say I wanted to try and enumerate all these local maximum, and then just check those. Well, in one dimension, there are most n local maximum. Each point can generate at least one local maximum. But in two and higher dimensions, it gets a lot trickier. There's results showing that there can be at least n choose D, so at least on the order of n to the D different local maximum. Combine them together, that's more than the number of initial data points. It's at least that big. What's an upper bound? Well, it's not clear if the number is actually so finite, and it could be the best upper bound to date that we were able to find is 2 to the D, to the plus n choose 2, and D to the n local max. So there is an upper bound on it, but it is it's a pretty big upper bound. So this sort of approach seems to not work so well either. But our results will kind of give some bound on the you probably can imply something about the stable local max are sufficiently different. Okay, so our results for this, again, approximate mode problem are in 2D, we slightly improved the results of the Agrawal paper from Sausage by improving the log and the 1 over epsilon factor. And then we have algorithms in low dimension, which is near linear in n when D is a constant here. It's about n log n, where the n log to the O of dn. And in high dimensions, we get a result that's quasi-polynomial. So it's linear in D plus a term that's independent of D, but is quasi-polynomial in n here. So okay, great. So these are our results. Let me kind of give some intuition of hopefully you think these are interesting. I think the techniques are as well. So let's kind of walk through the main ideas. In 2D, we're basically just refining this technique of Agrawal. The same idea, we want to sample a point and then sample a radius and look at the depth. But instead, we notice that a Gaussian kernel you can decompose is decomposable on the axes or on any basis. And so I can pick an X distribution for the width independent of a Y distribution. And so basically, I can get an unbiased estimator of a kernel density estimate by picking a point and then picking a random rectangle where the X and Y coordinates are chosen independently. And so I do this a bunch of time with rectangles. It's same analysis before, and then I find the point of the highest depth in the rectangles, and it turns out this is easier to do than with disks, so I can do this a little bit faster. So this is n over epsilon squared times log squared n. So I, small improvement here is what is this observation. Okay, the story in low and high dimensions is a bit more interesting, I think. We start in low dimensions and solving this with a polynomial expansion of the kernel density estimate. We use this particular polynomial expansion. You notice it has an infinite number of these terms inside the product. So we're going to start and do a finite approximation of this, bound this sum up to some term ns, which I will state what it is in a second. And this will give an approximate guarantee that guarantee an error of the right scale that we need. And then from here, we need to kind of try and find a solution if there is one with respect to some threshold, right? Is the kernel density estimate above some threshold or not? And if so, find a solution. And Renninger's algorithm helps provide a way to do this. And a simplification of this to stay here, if I have find a solution to a polynomial inequality with degree d among k variables, then the runtime is O of d to the O of k, where the O of k exponent has not been resolved, but is O of k here. And then we want to choose a bunch of potential thresholds of what it could be, and we need like log n of these different thresholds to check to see if we can find a solution. Then if we set basically the degree to 2 times s, right, s about log n over epsilon, and k is equal to d, then we can construct a bunch of these systems of inequalities, and this will approximate the kernel density estimate. So everywhere, right? I need to construct for each of the points in some region not too big around those points. I need to construct this system of inequalities, and so it takes me O of n time to construct each system near each of the points, and I solve, and I can then solve this in s to the O of d time around each of the points. So this gives a total runtime of n squared log n to the d to construct all the systems, and then n times log n to the O of d to solve each of these n systems. So this is pretty close to the right answer we want. There are a couple more tricks, and I want to point out one interesting one where we get rid of this how we get rid of this n squared factor. So it really is near linear for constant d. And the observation here is that we can say that we can restrict that we only need to look at the points nearby. If we get points that are very far away, the cost of the effect of the kernel goes to 0. So we only need to look at points in some neighborhood of size, basically square root log n. So to evaluate at this red point here, we only need to look at the points in this green neighborhood. And in fact, for all the points in that green disk, if we expand the neighborhood into this purple disk, then if we include all the purple points in this system of equations, then that gives a good approximation for the kernel density estimate for all the points in the green disk. Okay, so then what we can do is we can tile the region, the union of balls, sufficiently big balls, with these green disks, and for each green disk we put a purple disk around it. And for each purple disk we build a system of equations, and we can argue that each point is in a constant number of these purple disks. And so since it's in a constant number of these, the amortized cost into the system of equations is kind of, it only goes into a constant number of these systems. And so we don't get this n squared term anymore. We get a near linear term here. It's n times log n to the O of d. Okay, so this can be refined a bit with some ideas around core sets for kernel density estimates, but this is the main bound here. Okay, so this is our result in low dimensions. In high dimensions, the kind of the framework we're going to use, I think initially seem fairly standard. We're going to start at high dimensions, do a JL random projection to low dimensions, and then use our technique in low dimensions to solve it. But there are a couple of tricks here. We need to show that the result actually implies a result in high dimensions. And we need to recover the actual solution in high dimensions. And for that, we're going to use what's a single step of what's called the mean shift algorithm, which is a heuristic for kernel density estimates. Okay, so this is a standard Johnson-Lindenstrass guarantee for endpoints in RD. We want to do some sort of projection into m1/epsilon² log n dimensions, and we get this sort of the distortion guarantee. And you'll notice that we will use it so it's not symmetric. It's exact on the lower side and 1 plus epsilon on the upper side. And you'll see why in a second. And we want to apply this to this maximum function, right? That the cost of the maximum function is approximated by the cost of the projected version of the problem, of the maximum of the projected version of the problem. To get the left-hand side of this bottom, we use the right-hand side, the 1 plus epsilon, right, which is kind of the standard form. And this goes through with some calculations. It's not too hard. The part on the right, it turns out it's a little bit trickier, and this is why we use this slightly non-biased form here, is that we need to guarantee that the solution we find is also kind of represents a valid solution in the high dimensional space. And to use this, we need to use Krusbaum's theorem, which talks about if we define a finite map over a point set to low dimensions, that is Lipschitz, then there exists a continuous map over all of Rm to Rd, which is also going to be Lipschitz. And we can use this idea of this map in our setting in order to kind of get this right-hand side guarantee as well. And this is sufficient to see that the solution we find is a good approximation of the cost function in the high dimensional space. Okay, and so far the runtime goes, right now it takes just a standard Gaussian random projection, takes about ND times down to get to low dimensions. And then when we run the low dimensional algorithm, that the exponent, which was O of D, is now O of M, which is independent of D, right? So this is the main idea here. And we can attune this a little bit using some core set ideas I'm not going to go through. But then the overall runtime bound, that this can be tuned a little bit. Now it has the D separated from the expensive, the quasi-polynomial term on the right. Okay, there's one more thing we need to address, though. We did not find an actual approximate mode. We didn't find an approximate solution. What we're going to use is one round of what's called the mean shift algorithm. And this is a classic heuristic for trying to solve these, the mode of a kernel density estimate or any distribution, is that I take a kind of a weighted average of a point I think could be the mode based on all the points nearby, and I kind of update this guess to the weighted average, where the weight's determined by this kernel function. And so we are able to show, which might be folklore, but we provide a proof that this always increases the cost. So that if we do this with the weights we found in low dimension and apply it in the high dimensional setting, well, that will give us a result which is at least as good as the one we found in low dimensions, and it guarantees, and it gives us a point in high dimensions which has the appropriate guarantees with respect to the true optimal. So great. So in summary, basically for epsilon approximate mode with epsilon constant, it takes n log squared n time in 2D, near linear time in constant dimensions, and in high dimensions, it's ND plus a quasi-polynomial term in N, but independent of D. Great, so I will stop there and